Hey y'all, welcome back. Tonight's homework we are reviewing for the Unit 3 test, which is all about the chain rule, and we'll do a lot of graph analysis, trying to make connections between the graphs of f, f prime, and f double prime. But first, let's just review what the chain rule is. I'll go ahead and write that over here. Now, if you have a composite function, like let's say f of g of x, and we want to differentiate that, we need to differentiate first the outside function, leaving what was inside the parentheses alone, and then multiply that by the derivative of the inside function. Now, if we happen to have three nested functions or more, you'll just differentiate each function that's sort of inside the previous function last. So like if x here was a function like h of x, this would still be h of x here, and then finally we'd multiply by the derivative of h. So 1a has really two nested functions here. Our outside function is going to be this something to the 7th power, and our inside function is this 2x to the 5th plus 8x squared plus 3. So first we're going to differentiate the something to the 7th power. F prime is going to be, now differentiating x to the 7th will require the power rule. We'll bring down the 7 times the 2x to the 5th plus 8x squared plus 3 raised to the 6th power. Notice that what was on the inside of the parentheses stayed the same. Okay, maybe I'll highlight that. This is still the same thing as what we originally had. And so now we're going to multiply this by the derivative of what's on the inside. And we'll just use power rule all the way down. So we're going to get 10x to the 4th plus 16x, and that's it. Make sure, though, you have this second derivative here. No, not second derivative, but, well, it's the second thing we've taken the derivative of. It's not the second derivative. But the derivative of the inside function here, make sure you put that in parentheses. You might be on the safe side, try to be on the safe side and just always put it in parentheses. Sometimes you don't need to if it's just a single term, but if you put it on there always, you'll never forget to put it on when you need it. So yeah, that's it. Letter B is going to have, looks like two, we're going to have one outside, one inside function for this one. Our outside function is going to be 5 times cosine something, and my inside function is going to be e to the x plus 2 sine x. So we'll use the chain rule here, first by differentiating that 5 cosine x, which would be negative 5 sine of all that stuff that's inside the parentheses, e to the x plus 2 sine x, times the derivative of what's on the inside. So I'm going to put that in parentheses. The derivative of e to the x is just e to the x, and the derivative of 2 sine x will be 2 cosine x. Letter C also just has two functions that we're going to differentiate. This is a composite. We've got the first function is 3 e to the x, and then the second function is this tangent x. So the derivative of 3 e to the x is just 3 e to the x. So f prime is just going to be 3 times e to the tangent x times the derivative of tangent x. This is a case where you really don't need that set of parentheses, but it doesn't hurt. I would probably just recommend just always putting those parentheses there. That way you don't have to think about whether or not you need them. Okay, there's number 1. Number 2 says the function f is given by this algebraic function, this polynomial. At what values of x does f have a relative maximum? So let's make sure we know what we're looking for here. A relative maximum occurs when f prime goes from being positive to negative. In other words, we're looking for where f switches between increasing and decreasing. So to find that, we're going to find the derivative of f. So f prime, using the power rule, will be x squared, because 3 times 1/3 is 1, plus 2x minus 24. To find the critical values of f, we set the derivative equal to 0, and then solve. And I can solve by factoring this into x plus 6 times x minus 4. And I get two critical values. Maybe I'll label this. My critical values are at x equals -6 and x equals 4. These are the numbers that we'll place on our number line, our little sign chart here. I like to label the line with which function we're actually evaluating, just so that I can keep track. And here we want to be evaluating using f prime. Specifically, I'm going to be using this factored form to find the intervals of increasing, decreasing. So the partitions that I'll mark are going to be at -6 and 4. These are the critical values. These are locations where we potentially have a sign change, but you do need to test to check for the sign change. So if I plug in a number like -10, which would be in that first left-handmost interval, I would get a negative times a negative, which is positive. If I plug in a number in the second interval, any number between -6 and 4, so for example 0, I get a positive times a negative, which is negative. And then if I plug in a number like 10, which will be on that right-handmost interval, I'm going to get a positive times a positive, which is positive. So on the graph of f, so maybe I'll make a little number line above here. For f, the function is increasing, so it's going up, and then the function starts to decrease, and then it increases again. Well, I didn't do the decreasing all the way. And then it increases again. So notice here we have got a relative max at -6 and a relative minimum at 4. This question is asking for the x values of the relative maximum, so that's going to be at -6. And on the test, you'll be asked to justify all your answers on the free response section. So I'll just go ahead, and even though, oh, actually this one does say specifically justify your answer, but even if it doesn't, I'm going to go ahead and do that. So x equals -6 is a relative maximum, and you could abbreviate as long as you're getting your point across, because f prime went from being positive to negative. Number 3, it says let the graph the graph of the function f consisting of two line segments is shown in the figure below. Let g be a function given by g of x is 2x plus 1. Okay, so g is going to be this linear function here. H be a function given by f of g of x. So that's going to be a composite. Anytime we see a composite, most likely we're going to have to be working with the chain rule. Find the equation of the line tangent to the graph of h of x at x equals 1. Okay, we've done so many of these that you should be able to almost put yourself on autopilot to answer this one. To find the equation of a tangent line, we need a point, we need a slope, and then we'll put both the point and the slope into our point-slope form of a linear equation, y minus y1 equals m times x minus x1. So we want the tangent line to, we want the line to be tangent at x equals 1. So 1 is going to be the x-coordinate of the point. To find the y-coordinate, this y1, we're going to evaluate the original function, h, sorry, not f, but h at 1. And then to find the slope, our m, we're going to evaluate the derivative of h at 1. So we need to find, well, let's start with y1. So to find y1, and here, I'm going to erase this, break this down a little bit more like this. Say y1 is h of 1, and then m is h prime at 1. So first we'll evaluate h of 1. H of 1 is f of g of 1. Now g is 2x plus 1. So this is going to be f of 2 times 1 plus 1. 2 plus 1 is 3. So this is going to be f of 3. And we can find f of 3 from the graph. Here's 2, here's 3. F of 3 is 0. So that means the y-coordinate is 0. To find the slope, first I need to find the derivative of h. So h prime, and I only need to use chain rule here, is f prime, or the derivative of f in terms of g, times the derivative of g. So h prime of 1 would be f prime of g of 1. We evaluated that earlier, so we won't have to do that again, times g prime of 1. Okay, so f prime, we said g of 1 was 3. We found that over to the left when we found the y1. G prime of 1, well, we need to find g prime. Okay, so if g is 2x plus 1, g prime is 2. So actually, it doesn't matter where we're evaluating g prime, it's always going to be 2. So times 2. Now the slope of f at 3, we need to use a little rise over run action here to change in y over change in x. So I'm going down 6 over, what is that, 1, 2, 3. So the slope is going to be negative 2. Right? If I'm going down 6 to the right 3, negative 6 divided by 3 is negative 2. So the slope of f at 3 is negative 2. So I've got negative 2 times 2, which is negative 4. Okay, so my slope is negative 4, and now I can plug everything I need into this equation. Y minus 0, and you don't really necessarily need the 0, but I'm going to leave it there just so that I can stay consistent on my templating, equals negative 4 times x minus 1. And there's your equation. Number 4 says if f is a function defined by this quintic function right here, what are all the x-coordinates of the points of inflection? So the points of inflection are going to occur when f double prime changes sign. So what we need to do is find f double prime, construct a sign chart, put the subcritical values on that sign chart. Those will be where we potentially have a point of inflection, and then figure out where, if at all, the points change sign. So let's first find the first derivative, and we can use the power rule to do that. We get 15x to the fourth minus 20x cubed. And now we can use that to find the second derivative, which would be, let's see, 4 times 15 would be 60, and 3 times 20 is also 60. How about that? So to solve this, to find the subcritical values, we're going to set this equal to 0 and factor out a 60x squared, which will leave me with x minus 1. We'll have two critical values here, one at x equals 0 and one at x equals 1. These are called the subcritical values, as opposed to the critical values that we find on the first derivative. Subcritical values. So we're going to construct a number line, and this is going to be for f double prime here, because that's what we're interested in. We'll put 0 and 1 on this number line, and now we'll start to just start substituting numbers in. If I substituted a number like negative 1, I'm going to get a negative. I'm plugging these x values, by the way, into this expression right here. The factored one is usually a little... Sorry about that. A little easier to do mentally. And also because this 60x squared has the x as being squared, that's always going to be positive. So I really only need to concern myself with the x minus 1. If I plug in something like 0.5, 0.5 minus 1 is negative. So it actually continues to be negative here. So while 0 is a subcritical value, we do not have a point of inflection there because the sign doesn't change. Okay, so no point of inflection there. After 1, if we plug in a number like 5 or 10 or any number bigger than 1, we will get a positive value. So we do have a sign change here from negative to positive. And the points of inflection can either go from positive to negative or negative to positive. Either way, we do have a point of inflection, and the only one we have here is at 1. So our answer is C. Number 5, find the derivative. This is just a straight chain rule problem. So I'm going to rewrite this. It might be a little easier to kind of look at it as sine of x squared, all that cubed. Okay, so think about it like this, and if you think about it like this, you can a little bit more clearly see that our outside function here is x cubed. Now our inside function is also a composite. So the very inside function is x squared, but we have this middle function of sine. So we'll have to differentiate all three of these. Start with the outside function. Y prime is going to be 3 times sine of this thing squared, and I'm actually just going to go and revert back to putting the squared here just so that it looks more like the answer choices of x squared. So just use power rule with the 3. And then times, again with the bells, sorry about that, times the derivative of sine. So the derivative of sine is cosine, so this is going to be times cosine of x squared. And then times the derivative of x squared, which would be 2x. Now, if this were a free response question, I'd be perfectly happy with this answer. But notice how none of the answer choices look exactly like this. The answer choices are going to have, it looks like the coefficient and the x out to the front. So we're going to pull this 3 times 2x out to the front so that it looks a little bit more like our answer choices. 3 times 2 is 6. So this will be 6x times sine squared x squared times cosine of x squared. And we see that our answer is E. Number 6, we've got a sketch of a graph here. And it says on the given graph D, on the given graph, D is a relative minimum. Okay, so the slope here is going to be 0. Point C is a point of inflection. Okay, so that's going to be a change in concavity, meaning like it's going to be concave down right up until C and concave up afterwards. For each point on the graph, classify f prime and f double prime as being positive, negative, or equal to 0. So let's start with just f. Okay, so for f is going to be positive above the x-axis and negative below the x-axis. And f will equal 0 on the x-axis. So point A is on the x-axis, so this is going to be equal to 0. Point B is above the x-axis, so it'll be greater than 0. Point C is below the x-axis. It's negative, that'll be less than 0. D is also below the x-axis, and then E is back above the x-axis. So that's how we'll determine if f is positive or negative. Now, to determine if f prime is positive or negative, we'll be looking at the slope of the graph. So I'll go ahead and highlight this, and we can see that the slope is going to be positive up until this local maximum, and then also after D. The slope will be negative whenever f is decreasing. So from that local maximum to the local minimum. And then at the local extrema, so whatever this point is, and then D, the slope is 0 because we have a horizontal tangent line. Okay, so A is going to be on an increasing part of f, so the derivative is going to be positive. B is on a decreasing interval, so it'll be negative. C is also on that decreasing interval, so it's negative. D is a local extreme, specifically a minimum, and so the derivative will be 0. And then finally, E is on an increasing piece, so it's going to be greater than 0. F prime will be. So now let's talk about f double prime. F double prime is talking about the concavity, which changes at the point of inflection. And the problem tells us that C is that point of inflection. So we have one interval that's concave down from negative infinity to C, and one interval that's concave up from C to infinity. So A is on that concave down interval, so the second derivative is negative. B is still on that concave down interval, so that's still negative. C is on the concave, actually no, C is the point of inflection. So this one's going to be equal to 0. D is on a concave up interval, so the second derivative will be positive, and the same is true for E. So just to kind of sum up here, to find the sign of F, you're going to look either above or below the x-axis. Okay. To find the sign of F prime, we're going to be looking at the slope of F. And to find the sign of F double prime, we're going to be finding the concavity of F. And so that's how all those functions are related. Okay, well that's about it for 6. Let's take a look at 7. It says, given that F is this cubic function, determine the intervals for where F is concave up. Now we just got done talking about that. F is concave up when the second derivative is positive. That's really going to be our justification, is right here. That's what it means to be concave up. So what we need to do is find when that happens. And so we'll solve this extremely similarly to how we solved number 4. We're going to use that second derivative test. Or I guess really this is not the second derivative test, but it's kind of related. So we'll find the second derivative by first finding the first derivative, which will be 3x squared minus 6x. And then differentiating one more time gives me 6x minus 6. So to find the intervals where F is concave up or down, we need to find where F double prime is positive or negative. To do that, we're going to create a number line chart and put the subcritical values on here. We haven't found those yet, but to find those, we set the second derivative equal to 0, and then solve this equation, and we get x equals 1. Oh, I just realized I made a mistake. Let's back this up a little bit. The first derivative, I just saw this, 2 times 6 is actually 12. So I'm going to have to fix this. This number is going to be 12, which means this is going to be 12. Yeah, that's going to change our answer here, which means this over here would be 12, and then dividing both sides by 6 actually ends up giving me 2. Ooh, glad I caught that. So yeah, that should be 2. Okay, so let's try this again. Now, if I substitute in a number smaller than 2 into 6x minus 12, which is the second derivative, so plugging in a number like 0 is going to give me a negative result. Plugging in a number like 10 will give me a positive result. So F is concave up from 2 to infinity. Maybe I'll say F is concave up on the interval 2 to infinity, and I know that's true. My justification is because F double prime is positive. Number 8 is giving us this kind of crazy graph here. Yeah, this point looks like it should not be there. This might have been an issue with printing this. Let's see. I believe that point is supposed to be here. So let's get rid of that. I believe that, I don't know. I don't know how that happened. But yeah, it's supposed to be there. Just to basically show you that that 0 is negative 1. Okay, so it says, what are the critical values of f of x? We can see that it's at negative 7, negative 1, and 8. No. What am I doing here? Let's try this. Oh, no, it is. Yeah, I take that back. Wow. 7, negative 1, and 8. Okay, critical values, to be clear, are places where f prime is 0 or undefined. Okay, since this is a graph of f prime, we're going to list all those x-intercepts. So -7, -1, and 8. Now, -9 and 9 are the endpoints, and technically those are locations where f prime is undefined. I'll make sure that the way that I word this question is a little clearer on the test, but like technically -9 and 9 should be critical values because the function is undefined, f prime is undefined there. But typically also these questions are going to ask for open intervals, so you wouldn't include them. I wouldn't worry too much about that. As long as you got -7, 1, and 8 and you understand why those are answers, you'll be in good shape. What intervals is f decreasing? Okay, well, f is decreasing. And actually, just to, I think I'm going to erase that -9 and 9. I don't want to leave those there because I don't want to confuse you too much. On what intervals is f decreasing? So f will be decreasing if f prime is negative. Okay, that's what it means for f to be decreasing. And we see there's only one interval where that happens, and that's between -1 and 8. Okay, our justification is because f prime is negative. C says determine the x values of the relative minima of f. Justify your answer. So a relative minimum is when f prime goes from being negative to being positive. And we can see on the graph of f prime, that's going to happen exactly once at x equals 8. You can see the graph is negative and then goes positive. So we should expect that on f, we have a relative minimum. So the x value is going to be at 8. And that's because f prime went from being negative to positive. D says determine the intervals on which f of x is concave down. Concave down means that f double prime is negative. So the slope of f prime is negative. So if we're looking at this graph, we're looking for where the slope is negative. We can see that here and here. We're going to have two intervals. So we've got one from -9 to -7, and also from -5 to 4. And that's because f double prime, it says justify your answer using f prime. So, normally I would say it's fine to just say second derivative is negative, but if we're going to have to reference f prime, we want to say because the slope of f prime is negative. Okay, yeah, I guess that wraps it up for this page. Let's go on to the next one. And it's totally blank. What's going on here? Let me try to refresh. And there we go. Did we miss anything? No, we're good. Okay, number 9 says if natural log, or if f of x is the natural log of x plus 4 plus e to the -3x, determine f prime, and then go ahead and find f prime of 0. So first let's find f prime. So f prime is going to be, we're going to have to use chain rule here, 1 over x plus 4 plus e to the -3x times the derivative of that expression. So the derivative of x is 1, the derivative of 4 is 0, the derivative of e to the -3x would be e to the -3x times the derivative of -3x because of the chain rule, which is -3. Okay, so just to kind of clean that up a little bit, and I'm actually going to put that whole expression over here, since times 1 would just be itself. I'm going to put it in the numerator, just maybe that'll make the arithmetic a little easier. So I've got 1, minus, so the -3, minus 3 times e to the -30x power, all over x plus 4 plus e to the -3x. So that's our derivative, and now we want to find f prime of 0. So f prime of 0 is going to be what I get when I plug in 0 everywhere. So I'm just going to rewrite the entire thing, but replace all the x's with a 0. All right, so let's start simplifying. Now, anything to the 0th power is just 1. So for that numerator, we have 1 minus 3 times 1. 1 minus 3 is negative 2. And then on the denominator, we've got 0 plus 4 is 4, plus anything to the 0th power is 1 again. So it's going to be negative 2/5. Number 10 says f prime is defined by this polynomial function. Okay, looks like it's a 6th degree? Yeah. And it says f of x says which of the following relative extrema? So first, we're going to have critical values at, and I'll start my number line chart here, at 2, 3, and 4. So 2, 3, and 4. And this is a number line for f prime. Now I'll plug in some numbers, some representatives from each one of these intervals to see what's going on in that interval. So if I plug in a number like 0, I'm going to get a negative. Now this squared term right here, this expression is always going to be non-negative. So multiplying by that, I'm not going to be really worried about that because multiplying by any positive number is going to stay whatever sign it originally was. So I'm really just going to look at the x minus 2 and the x minus 4. So if I plug in a number like 0, I get a negative times a negative, which is positive. If I plug in a number like 2.5, I'm going to end up with a negative value. Plugging in 3.5 results in another negative value. Plugging in a number like 10, we'll have a positive times a positive is positive. So to try to break down what's going on here, the slope of f changes from being positive to negative, indicating we have a relative max at 2. At 3, we've got a negative slope, followed by another negative slope. So this is going to be neither a max or a min. And then at 4, we have a negative slope, followed by a positive slope. So this is a location where we're going to have a minimum. So let's take a look at all of our, okay, there we go. What's going on here? Let's take a look at all of our choices. First one says a relative maximum is at x equals 2. We have verified that's true. A relative maximum at 3, no, we saw that that's not going to be a maximum or a minimum. And then at 4 says a relative maximum, but that's not right. It should be a minimum. So the only correct answer here is the first one, and so our answer is A. Number 11 says given the position of a function, given that the position of a function is given by this nice little equation here, determine the velocity at the time when the acceleration is equal to 0. So the velocity is the derivative of at the position. So v of t is equal to x prime. And that's going to be 9t squared minus, what would that be, 36t. So that's the velocity equation. Now let's find the acceleration equation, which is the second derivative of the position, or another way to think about it is it's the first derivative of the velocity. So all these three functions are basically the same thing, and it's the derivative of the expression we just wrote. So that's 18t minus 36. So we're going to find at what time was the acceleration 0, because it's asking for at the time when the acceleration is equal to 0. So we'll set 18t minus 36 equal to 0, add 36 to both sides, and divide both sides by 18, and we get t equals 2. So this is the time that we're interested in. It says determine the velocity at that time. So we have our velocity equation right here. So v of 2 is going to be 9 times 2 squared minus 36 times 2. So I get 9 times 4 minus 36 times 2 would be 72. 9 times 4 is 36. So we have 36 minus 72, which is negative 36. So that's going to be our answer. So let's see. The velocity It's going to be negative 36. What are our units here? Doesn't even give us units, so we're just going to go ahead and say it's negative 36. Normally it'd be something like meters per second or something along those lines, miles per hour, whatever units are given, but this one just for whatever reason did not give any units, so we don't want to just arbitrarily place some units on top of it. Number 12. The function f has a property that f prime, and f double prime are all negative, are negative for all real values of x. Okay, so the fact that f is negative, let's just break down what each one of these mean. F being negative means that the graph should be below the x-axis. So right away we can say E is not going to be our answer. F prime being negative means that the slope is negative. Okay, so if we see any positive slopes, that can't be our answer either. So C is positive slope. A has positive and negative, but this is always going to be negative. So that leaves us with B and D. And lastly, the fact that the second derivative is negative, that tells me that the graph is concave down. Okay, we can see B looks to be concave down. D is concave down to a point, but then is concave up. So it's not going to be D. Our answer is B. Number 13, we're going back to the good old chain rule. Hope you guys are ready for this. Now, this is going to have not only the chain rule, but the product rule as well, because we're multiplying sine by e to the 5x. So let's get that. So this is like my f, and this is my g, and I know the product rule here is the derivative of a product is equal to the derivative of the first times the second, plus the first times the derivative of the second. So let's break this down. Y prime will be the derivative of the first. So that'll be cosine of 2x plus 4 times the derivative of 2x plus 4, which would be 2, times g, so that's times e to the 5x, plus f, which is sine of 2x plus 4, times g prime, which would be e to the 5x times 5. And that's our answer. Don't worry about simplify. Okay, it even says you do not need to simplify. B, we're going to have to use chain rule again, but also need to use the quotient rule. So if we want to find the derivative of a quotient, we're going to multiply the derivative of the top by the bottom, subtract the top times the derivative of the bottom, all divided by the bottom squared. So here we're actually going to need to use chain rule first. So we're going to have 6 times that quotient raised to the 5th power times the derivative of the quotient. And this is where the actual quotient rule comes in. So the derivative of the top is 3. So 3 times x squared plus 5 minus the top is 3x times the derivative of the bottom, which is 2x, all over x squared plus 5, all that squared. Again, don't worry about simplifying. In fact, you're just doing yourself a disservice if you try to simplify too much. C is secant of 3x. Now the derivative of the secant is secant tangent. So this is going to be secant of 3x times tangent of 3x times the derivative of 3x, which is 3. I guess the hardest part of this one is just remembering the derivative of secant. All right, D says f of x is the square root of 5x minus cosine of x. Remember that when you take the square root of something, that's equivalent to raising it to the 1/2 power. So if it helps, just rewrite this as 5x minus cosine x to the 1/2 power. So f prime will be 1/2 times 5x minus cosine x to the negative 1/2 power times the derivative of the inside, which would be 5 plus sine x. And that's it. Number 14 says determine the equation of the line tangent to the graph of that cubic at its point of inflection. You must show your work. All right, so we've answered equation of the tangent line questions so often this year that you should know exactly how to start setting this up. We'll start with a point. It's going to be our x1, y1, and we're going to need a slope. And then once we have that point and that slope, we can substitute everything that we know into y minus y1 equals m times x minus x1. So the real tricky thing about this one is that all the problems that we've worked on so far gave you an x value to work with. And this one does not give you an x value, unfortunately. You've got to find the x value of the point of inflection. So that point of inflection is going to occur anytime the second derivative changes sign. Okay, so when it goes to positive to negative or vice versa, either way, it's a point of inflection. So let's find that second derivative. We'll start with the first derivative, which is 3x squared minus 6x. I'm just using power rule here. And then the second derivative will be 6x minus 6. So I'm going to construct a number line chart, and I'm going to put my subcritical values on it. And this is for y, not f. It's not called f this time. It's called y. So for y double prime. And so yeah, let's find those critical values, those subcritical values. The subcritical values are going to be where we will potentially find points of inflection. We need to double check and make sure that happens, but they will occur anytime the second derivative is 0. So if I solve this equation by adding 6 to both sides and dividing by 6, I get x equals 1. And so now I'm going to test values on either side of 1 to see whether or not the second derivative is positive or negative. And I'm kind of hoping it is, because otherwise we won't have a point of inflection, and this question will be unanswerable. So I'm kind of assuming it's going to be 1, but let's just double check. If I plug in a number like 0 into 6x minus 6, that's going to give me a negative value. If I plug in a number like 10, it's going to give me a positive value. So sure enough, we do have a change in sign on f double prime. So that means that our point of inflection is at x equals 1. So that's going to be the point that we're going to use. That's going to be the x value, or the x coordinate of the point where we're going to find this tangent line. So to find the y coordinate, we need to find the value of y when x is 1. So my y1 is going to be, 1 cubed minus 3 times 1 squared plus 2. So that's going to be 1 minus 3 plus 2. Is that just 0? Yeah, I guess that's just 0. So my y1 is going to be 0. And then my slope I'm going to find by plugging in 1 into the derivative, y prime. So my slope here, let me just kind of move all this stuff over a little bit. Oops. Just give myself a little bit more room here. So yeah, my slope, my m, is going to be the value of the first derivative at x equals 1. So 6 times 1 minus 6. Is that 0 also? Hold up. 0 times 1 plus 6. Yeah, I guess that's 0 also. Oh, wait a minute. I'm looking at second derivative. I'm like, there's no way that's going to be true. Okay, sorry. Yeah, we want to plug it into the first derivative, not the second derivative. I think I even said that. I don't know why I started plugging it into 6x minus 6. So 3 times 1 squared minus 6 times 1 is going to be 3 minus 6 is negative 3. So yeah, my slope's going to be negative 3. And now I'm ready to write my equation. Y minus 0, and I'll just leave the 0 there. You don't necessarily have to write it, but just want to stay consistent with how I'm writing all of these tangent line equations. And there you go. There's the equation of the line that's tangent to the graph of that cubic at the point of inflection. So kind of what I'm imagining this graph looks like. I don't know exactly what it looks like, but basically what we just found was if we imagine this graph does something like this, right? I know it's going to be concave down and then concave up based on this sign chart. that point of inflection, like right here where the concavity changes, we're finding the equation of that tangent line, or the line tangent to the curve at that point, which is going to look, something like this, okay? And what we just found was the equation of that line. It should have a negative slope because, just look at the graph, right? The slope there is negative. So anyway, I just want to give you a little visual there to accompany your equation so you could have a decent idea of what it is we actually just found. Number 15 says f prime is this, 1, 2, 3, 4 quartic function. Which of the following are true? Okay, the first one says f has a local maximum at x equals 3. Okay, so this is all talking about local max and local min. So we're going to use the first derivative test and find our local extrema. So my critical values here are going to be 0, 2, and negative 3. So I'm going to set up a little number line chart for f prime with negative 3, 0, and 2. And then we're going to start plugging in some values for each of those intervals. So if I plug in a number like negative 5, I'm going to get a positive value. If I plug in a number like negative 1, I have a negative times a positive, which is negative. And just like with a lot of problems we've worked before, you can kind of ignore this x minus 2 squared. Because it's squared, it will always be positive, and multiplying a number by a positive number is not going to change the sign. So if I plug in a number like 1, I get 1 times 4, which is positive. And if I plug in a number like 5, I'm going to get a positive times a positive, which is once again positive. Okay, so let's just let's summarize what we know from this sign chart. This is the graph, or this is a sign chart for f prime. So if f prime is positive, that means f is increasing. If f prime is negative, then f is decreasing. So what that means is we've got a local max at negative 3. And then at 0, the slope, or the value of f prime, is changing from being negative to positive. And so at 0, we've got a minimum. And then at 2, the slope changes from being positive. It does go to 0, but then it goes back to being positive. So this is going to be neither. It's neither a max nor a min. Okay, so let's look at these statements. We have a local maximum at x equals negative 3. Well, yeah, that's for sure true. And then do we have a local minimum at 0? Sure do. So it's going to be 1 and 2. So we can cross out A, B, and C here, and we just need to test to see if the last one's true. It says f has neither a local max or local min at 2, and sure enough, that is true as well. So our answer is E. Number 16 says the graph has a point of inflection at 1, negative 6. What is the value of B? Ooh, this is a tough one. I like this one. So we know it's got a point of inflection at 1, negative 6. That means at 1, we have a sign change on the second derivative. So let's figure out what B and A are here. So first, let's find the first and second derivatives. The first derivative, y prime, will be 3x squared plus 2ax plus b. And y double prime is going to be 6x plus 2a. Now we know we've got a point of inflection at 1, negative 6, which means that when x is 1, the sign is going to change. So we have so y double prime is going to be 0. Okay, so if y double prime is 0, at the point of inflection, x is going to be 1, and we can use this to solve for a. So we've got 0 equals 6 plus 2a. If we subtract 6 from both sides, we're going to get negative 6 equals 2a, and therefore a is negative 3. So now we know a, and we can use that to find b. Because if we go back to the original equation y, we know that we have a point 1, negative 6. So we could plug that into x and y. We can also plug in our a value, and the only unknown left will be b. So y is negative 6, x is 1, a is negative 3, x is 1, b is what we're trying to solve for, and there you go. Here's our setup. We're going to solve this for b. So negative 6 equals 1 minus 3 plus b minus 6. Okay, 1 minus 3 is negative 2, minus 6 can be negative 8. So negative 6 equals negative 8 plus b. And if I add 8 to both sides, I get b equals 2. Number 17 says, let f be the function defined by this cubic here, on which of the following intervals is the graph of f both decreasing, meaning the first derivative is negative, and concave up, meaning the second derivative is positive. That's your justification. All right, whatever interval we end up saying here, my justification is both that f prime is negative and f double prime is positive. So we're going to need two number lines, and we'll try to find where the overlap of those two number lines are. So let's find our critical values for f prime and our subcritical values for f double prime. So let's first find f prime. That's going to be 6x squared minus 6x minus 12. F double prime is going to be 12x minus 6. Okay, so for our critical values, we're going to set this equal to 0. We can factor out a 6 as a GCF. And then we could factor, maybe I'll move this over a little bit, kind of running into my justification here. I want to move this too, I guess. There we go, that's a little better. So yeah, we could factor this as x minus 2 times x plus 1, and we're going to get x equals 2 and x equals negative 1. All right, so those are my critical values for f. So I'm going to go ahead and start my number line chart for f prime, okay, with negative 1 and 2 on it. I'm just going to leave that there. We'll come back to the sign charts, but I also want to try to find a number line for f double prime. So for f double prime, we're going to find the subcritical values by setting f double prime equal to 0, adding 6 to both sides, and then dividing both sides by 12. So I get 1/2. It's going to be my only subcritical value. Okay, so now let's go ahead and construct our sign charts here with pluses and minuses. Let me move this slightly up a little bit. So yeah, if we plug in a number like negative 3 into f prime, and really I'm going to focus in on this. Oh, can't really see that. I'm going to use this equation here, the factored form. So plugging in a number like negative 5 is going to result in a negative times a negative, which is positive. And then if I plug in a number like 0, I'm going to get a negative times a positive, which is negative. If I plug in 5, I'm going to get a positive. Now looking at f double prime, I'm looking at this equation here, okay, 12x minus 6. If I plug in a number like 0, I'm going to get a negative number. And if I plug in a number like 10, I'm going to get a positive number. So what we're looking for is the overlap where f prime is negative and f double prime is positive. Okay, so I'll kind of highlight both of these. Okay, so f prime is negative, which means f is decreasing, between negative 1 and 2. F is concave up anytime f is concave up anytime the second derivative is positive. So that's going to be between 1/2 and infinity. And so in order for both of these to be true, we look for the overlap in these intervals, which we're going to see is right here. Green's probably not the best choice there. Blue and yellow are already making green. Maybe I'll use red here. It's going to be right in here. Okay, so it's going to be in between 1/2 and 2. Number 18 says g is a differentiable function such that g is negative. Okay, so g less than 0 means g is negative always. Okay, for all real numbers x. We also have an equation for the derivative of f, and it says determine the intervals on which f is increasing. Well, f will be increasing anytime f prime is positive. So we'll find the critical values of f, which will be where f prime is 0, and then create our number line chart, and we'll be looking for where it's positive. So f prime x is going to be equal to x minus 4 times x plus 3 times g of x. Now it says g of x is always less than 0, so it will never be 0, which means our only critical values here are going to be at x equals 4 and x equals negative 3. So when I construct my number line for f prime, those are the numbers I'm going to put on there. So to find the signs, you just got to be real careful that you also consider the fact that g of x is always negative. Okay, so whatever I multiply by those first two factors, I'm going to flip that sign because I have to multiply by that last negative. So if I plug in a number like negative 7, for instance, I'm going to have a negative times another negative. So 3 negatives being multiplied will result in a negative value. If I plug in 0, I have a negative times a positive times another negative, which is positive. And if I plug in something like 10, I get a positive times a negative, which is negative. So here's my sign chart for f prime. And the question's asking, where is f increasing? And it's increasing between negative 3 and 4. As far as my justification is concerned, I'm going to say because f prime is positive. And that brings us to our final question. The graph of a twice differentiable function, that just means that the second derivative exists. Yeah, maybe I should make a note of that. That's not like a big deal here. I mean, you're probably going to assume that anyway. But technically, we need to say this. So this just means that the second derivative exists. Which of the following is true? Okay, so at 2, let's talk about the value of f, f prime, and f double prime. Okay, so f of 2, we can see on this function, this is a graph of f, is exactly 0. Okay, it's on the x-axis, it's an x-intercept. Okay, just to be clear, this is f of x. F prime is talking about the slope. Now, we don't have an actual value here, okay, but we can see that the slope of the tangent line at 2 would clearly be positive. Okay, remember, this is the slope of f. And that slope is positive. F double prime, okay, we're really asking, wait, is this concave up or concave down? And we can see that because of the curvature here, anytime you have a curve that does something like this, it's like kind of half of that upside down u, that's going to be concave down. And so the second derivative is negative. All right, so the smallest number is going to be the f double prime. Okay, so that should be the smallest one in this inequality. So far, D and E are the only options. Followed by when, the 0, so f of 2 should be next. And then finally, f prime should be the biggest number because that's positive. So our answer here is D. And that wraps it up for this unit review. Thanks for watching. Y'all have a great day.